Welcome to your first lesson in Chapter 3, and this whole unit depends on exponential equations and their inverses, which are logarithmic equations. So we're going to start with exponential today in Lesson 3.1, and there was a paper that came with these notes. If you don't have it, you can go print that off through Canvas. First, I'd like to graph y equals 2 to the x. Now, if you'll notice, an exponential equation has the base as a constant, but it's raised to the variable. So remember, we talked about this. The x is in the exponent as opposed to a power function where it would be in the base. Let's graph this equation. If we let x be 0, 2 to the 0 is 1. If we let x be 1, then we're at 2. If we let x be at -1, then we're at a half. So it's doing this number right here. And it's going up. If we let x be 2, then I'm at 4. There we go. So we are going to graph that, and that is actually a growth. You see how it's increasing? That is a growth equation. And we're going to highlight that one blue. Now, if I make the exponent negative, then it does a little bit different. Can you guess? The exponent's negative, which means it's going to flip it and reverse it, reflect it over the y-axis. Remember, if the negative was out front, it would go over the x-axis. This is it with the x. So what we're going to do here is we are just going to flip it. 2 to 4. There we go. Well, let's make this one purple. So this, if it's not growth, it is decay. So we're going to make this one our decay, and let me underline that one so you know that that's the growth. Okay, this is the decay equation. Also, if you want to think of this, remember an exponent, if it's negative, that means you can put it down here in the bottom and it becomes positive. So that also equals 1 over 2 to the x, if you want to think of it that way in the denominator. All right, so let's look at the domain of these functions. All right, if I do just the growth, that domain is everywhere, right? So -infinity to infinity. And it's the same thing if I look at the decay. The range, the same value from 0 to infinity, correct? 0 to infinity. There's an asymptote there. We'll never hit that, the x-axis, y equals 0. The y-intercept, they both intercept at 0, 1. But they never have an x-intercept. Where is the growth increasing? Well, it's increasing everywhere, isn't it? So from everywhere, the domain. And the decay model is increasing anywhere? No. But it's decreasing on the entire domain. So those are flipped. Now we have an asymptote, we said, here at y equals 0, the x-axis. And your end behavior, you are well familiar with this. The limit as x is approaching, let's do just the growth, look at the blue, as x is approaching -infinity over here, then the function goes to 0. So let's say, as x is approaching -infinity, the function is going to 0. As it approaches positive infinity, the function is going to infinity. What do you think is going to happen on the end behavior for the decay model? Well, the left as x is approaching negative infinity, look over here at the purple, as x is approaching negative infinity, the function is going to infinity. But as it approaches positive infinity, the function is now going to 0. So that should have been a review, all right, but you need to get in your mind what the exponential equations, how they're behaving. Now, just like our other transformations, let's look at how this equation would be altered. So here is let me find a way to highlight the x. The x is right here in the exponent. And let's look at all these other values, what they're going to represent. Let's do this first, out front. That's pretty easy. The plus and minus out front reflects it. Do you remember? This is reflected top to bottom. All right, this is over the x-axis. And then this plus or minus with the x, like we set up there, that one, let's see, I'm going to take this way over here. This is reflected left and right, just like we did on the top of the paper here. That would be over the y-axis. Let me switch colors here. Let's go to green. Let's do some green. So if it is vertical, okay, this change right here is moving it vertically up or down. All right, if it's stuck out there on the end, it's up, it was positive. It was down, it was negative. All right, if it is this h, do you remember the h is moving it horizontally, left and right. But remember, this one's flipped, so this would be left was the positive and the right was the negative. All right, different color. Let's go blue. The number that's out front, the number out front of the exponent here, that one, do you remember which way that expanded it? Okay, if the a was greater than 1, it did a certain change, and if the a was between 0 and 1, then, so this was expanding, this was compressing. Remember, if it was vertical or horizontal. If it's out front, that's vertical. Vertically, vertically. So the C that's up with the X, that's it compressing and expanding it horizontally. Let's do that one. So if if C was between 0 and 1, or if C was greater than 1. So this expanded here, and this was compressing horizontally. The more you memorize the changes here, because they will apply to all the graphs we're going to do, even when we get into trig. So you really need to memorize how it's being shifted. All right. Now let's look at something very common when you're dealing with exponential equations, and that is what we call the natural base, or the number e. And I know that's strange because you would think e is a letter. But in mathematics, we use the number e, and sometimes it's like italicized, and that refers to a very special kind of number. First of all, it's an irrational number. Right? So it doesn't repeat in any sort of a pattern. And a little bit of a history here. This is named for a Swiss mathematician mathematician Leonard Euler. Scoot over a little bit. There you go. Now this number is used so much of the time, and since you have an understanding of limits now, we can write it with the limit. But if you take the limit as x approaches 0 of the sum of 1 plus x raised to the 1 divided by x, 1 over x, or think of it as the limit as x approaches infinity of 1 plus 1 over x to the x. That limit approaches this number. And the number is 2.718281828. It keeps on going. We usually will just say 2.718. This is so common. There is so many applications for this, and we even have a specific number or place on the calculator to shorten it for you. It's kind of like pi. They have a pi button. They have an E command as well. And what I'd like to do now is to look at some examples for this with the E, but to show how it applies to being translated. You can have an equation with an E that's translated. Let's look at this. Here are a few examples. If I wanted you to describe this graph, and if the original function is e to the x, right, so this 2.718 to the x power, and I want you to tell me how it has been shifted. Well, this first one, if the x is negative, if you need to look back at your notes, that means that it is reflected over which axis? It's reflected over the y axis. There we go. This equation that has this function that has e to the x plus 1 minus 5, so this is going to be your k, the 1 is the h, that 1 shifted it 1 unit to the left, so shifted 1 unit left and 5 units down. This one has a coefficient out front. Remember, that was the a in our other equation. So this expands it vertically by 3. Now what I'd like to do in part 2 is do some examples with exponential equations, because we have numerous applications for exponentials, and we'll do that in part 2. See you then.